So here we're going to take a look at the so-called conductive geotherm. This is the geotherm where heat, which we will write as Q, where heat is transferred by conduction rather than by convection or radiation. Now, where would that happen? Well, let's say we're standing here on the surface of the Earth. It would happen in the so-called thermal lithosphere. So the thermal lithosphere is that outer part of the Earth that is rigid and is cold enough that it doesn't move very easily. Underneath the thermal lithosphere would be the convective mantle. So the convective mantle is soft enough and hot enough that it can move around, and there heat would be transferred by convection. We're going to look at the way heat is transferred through this very cold, rigid part of the Earth called the thermal lithosphere. And when we calculate the temperature in that part of the Earth, we can use an equation that looks like this. So we'll have the temperature at some depth, Z, so Z is the depth of interest. And for our numerical example, we'll just use the case of 5 kilometers. And then Z naught will be our reference depth. So Z naught is a reference depth. And for our numerical example, we'll let that be the Earth's surface, and it'll be 0 kilometers. So the temperature at, let's say, some depth Z will be the temperature at our reference depth, Z naught, plus the geothermal gradient, dt dz, multiplied by Z minus Z naught, plus 1 over 2 factorial times the second derivative, and it'd be Z minus Z naught squared, plus some other terms that we could have if we like, where the last term would be 1 over n factorial, and then the nth derivative of temperature with respect to Z, and that would be multiplied by Z minus Z naught to the nth power. Now it ends up that all we need is this quadratic part. These extra terms here we don't really need, so we're going to ignore them. We call it quadratic because we have Z to the second power. And so the trick here, if we want to calculate the temperature at some depth, is simply to identify this first derivative and this second derivative. So what are they? Well, the first derivative of temperature with respect to depth can be related to things that we can measure. So we have J sub Q Z naught divided by lowercase k. This J sub Q, this is the heat flux. It is the heat flux measured at a depth of Z naught. So we can take some area of the Earth's surface and look at the amount of heat Q that's passing through that area, and that would be this thing here. J is for flux, Q means that we're measuring the flux of heat, and the Z naught identifies where we are measuring it. We're taking that measurement at our reference depth Z naught, which we're going to say is at the Earth's surface. Lowercase k is thermal conductivity. And that is a measure of how quickly heat will pass through a given kind of material. So we can have some Q, some heat being input to this side of the box, and we can look at how quickly it passes through that to let heat out on the other side of the box. And the thermal conductivity, that lowercase k, would be a measure of how quickly that heat is transferred. So that gives us the first derivative term here. What about the second derivative? This guy over here. So the second derivative is equal to minus A, again over thermal conductivity. We already know what this is. That's this fellow here. The A is heat production. It is the amount of heat that is produced by the radioactive decay of elements like uranium or thorium or potassium. As these radioactive elements decay, there's a certain amount of energy that is given off, and A is a measure of that heat that is produced in the process. So let's erase the chalkboard and rewrite our equation. The temperature at some depth Z is going to be equal to the temperature at a reference depth plus that first derivative, which can be written as a ratio of heat flux to thermal diffusivity multiplied by Z. We're going to let Z naught equal 0, so we don't need that extra term. and then it will be minus A over thermal conductivity, and then multiplied by Z squared. So that is our equation for measuring the geothermal gradient when heat is being transferred by conduction. Let's work in numerical examples so we can see how this plays out. So let's say the temperature at Earth's surface is 30 degrees centigrade. Rather warm, but it'll work. And let's say the heat flux, J, that we measure at Earth's surface is 45 milliwatts per square meter. So we have a square meter of area that we lay out on Earth's surface, and the amount of heat that's coming through that area is 45 milliwatts. For consistency with units, we'll convert everything to watts. So this would be 0.045 watts per meter squared. Thermal conductivity is, in our case here, 2.5 watts per Kelvin dot meter. So this K is a capital K for Kelvin. That is numerically the same as 2.5 watts when we express it in degrees Celsius per meter. And the reason why is that even though kelvins and centigrade are different from one another, if you look at the intervals on the Kelvin scale or the degrees centigrade scale, those intervals are exactly the same. So when we look at rates, as we have a change in going from 1 degree Celsius or a change in 1 degree Kelvin, those increments will be the same, so numerically there's no conversion that needs to happen here. And we've already got watts and meters, so we're good with consistency with this guy over here. And then our final term A, if we have a cubic meter of stuff, we can measure the amount of heat-producing elements in it, and a typical value might be about 2.95 microwatts per that meter cubed. And if we want to convert microwatts, that's a millionth of a watt. That would be 2.95 times 10 to the minus 6 watts per meter cubed. So let's put these into the equation and see what we get. So our temperature at 5 kilometers would be the temperature 30 degrees plus 0.045. We're not going to put in the units here because we don't have room. And that would be divided by 2.5 multiplied by 5,000. We need to have the depth in units of meters. And then minus 2.95 times 10 to the minus 6. That would be divided by 2. That's our 1 over 2 factorial term, multiplied by 2.5. That's our thermal conductivity term. And then multiplied by the depth squared. So again, in meters, that's 5,000 squared. These first two terms give us 120 degrees centigrade. All three terms, if we add them together, then we get 105.25 degrees centigrade. So that would be the temperature at 5 kilometers depth. We can do this calculation over a range of depths and calculate a geotherm where we plot temperature increasing with depth downward. And then we would get something like this, a little bit of a curve. We have a quadratic. Eventually it's going to turn around and become a negative geothermal gradient, positive in the way we've drawn this with depth going downward. But we would want to ignore that part of the equation. That might happen at a subduction zone, but that's not really the best way to model an inverted geothermal gradient at a subduction zone. So if you do make a plot like this, don't extrapolate the line anywhere beyond where it begins to become very steep or becomes a negative geothermal gradient. We can also calculate an average geothermal gradient. So the average geothermal gradient, at least for the top 5 kilometers, the way we've calculated it here, would be dt dz. We could take the temperature at a depth of 5 kilometers, divide it by 5 kilometers, and we'd get an average geothermal gradient of 21 degrees centigrade per kilometer. And sometimes it's useful to take that curve and approximate it as a straight line.